Hello, here are the reviews from the Friday the 13th homework. So we have two 50 milliliter solutions with a pH of 5. One is hydrochloric, the other is acetic. First question, which one has the higher concentration of acid? Well, you're going to need more acid, or more acetic acid, to reach a pH of 5 because acetic acid is a weak acid, so we're going to go with acetic acid for A. Which one has the higher percentage ionization of acid? Well, since hydrochloric acid is a strong acid, it ionizes 100%, so that has the higher percentage ionization of acid. Now let's think about C, the amount of 0.1 molar sodium hydroxide needed to neutralize the acid. So which one has the higher amount of sodium hydroxide needed to neutralize it? Well, since we have more acetic acid to reach a pH of 5, we're going to need more sodium hydroxide to neutralize that. And which one has a higher conductivity? Again, hydrochloric acid, strong acid, 100% ionization, so it's going to be the most conductive. For this question, is an aqueous solution of sodium hydrogen phosphate acidic or basic? We just need to compare the Kb to the Ka, and you'll notice that the Kb is bigger, so therefore it's basic. Calculate the pH, so on and so forth. Acetic acid is a weak acid. They gave you a Ka. That's a big hint that we're talking about a weak acid. So if you're talking about a weak acid, you need an ice chart. So if we go through here, we can ignore X. There's your hint. If Ka over the concentration of the acid is less than 10 to the negative 2, we divide them out. Then we could ignore X. Make sure you show the equilibrium expression. Solve for X. X gives us the hydronium ion concentration. And then from that we take the negative log, we get a pH of 2.8. Okay, so we have a weak base here. How do we know? Well, it's not a hydroxide of group 1 and 2 metals, and they give us a Kb. So let's take a moment and write out the ionization of ammonia. Okay, so here's the equation. I noticed on some of your work that we kind of didn't know what to do with a base. Now remember, a base is a proton acceptor. So what's happening here is that one of our hydrogens is being transferred to the ammonia for our product. So we get ammonium ion and hydroxide as a product. So be careful and watch out for that you actually write the equation correctly. Because if you write it incorrectly, you get an incorrect answer, which is what happened to quite a few of you on this homework. So be aware of how bases function. So now, since it's a weak base, we're going to do an ice chart. We have the Kb, so please pause the video, take a moment, and do your ice chart, and then come back and check and see what happened with it. Okay, here's our ice chart. Double check if everything looks good. Take a moment, decide, can we ignore X or not? Okay, if I divide those out, I get 2.4 times 10 to the negative 5th, which means, yay, we can ignore X and let's move on with life. Okay, write out the equilibrium expression, set it equal to Kb, and solve for X. Okay, when I solve for X, I get X equal to 0.00367. Now the question is, what is X? Hopefully you realize from up here, X is actually our hydroxide ion concentration. So that is 0.00367. And they want to know the pH. You have a couple of ways to do this. You can solve for the hydronium ion concentration and find pH that way. Or my favorite way is to find the pOH, subtract that from 14 to get the pH. So pause the video now, take a moment, and see if you can calculate the correct pH. So when it's all said and done, you get a pH of 11.6. So now we have an equation that you might want to remember. We could take our molarity, concentration of acid, times our volume of acid, and if we're looking at an equivalence point, those should equal the concentration of the base times the volume of base, because what happens is at the equivalence point we want the moles to be equal. The moles should be equal. So in this situation, they give us in milliliters. Most often when you're doing a titration, everything's in milliliters. So we can use this cool unit called millimoles, which is just concentration times milliliters would give you millimoles. And you'll see as we go through the problem that the way units will cancel, they want to know the molarity, so we'll just be getting a moles per liter situation, because we'll have millimoles per milliliter, same as moles per liter. So we have the equation. Why don't you start plugging some of the numbers in and see where you get. So there we have it. If we plug in the volume of the acid, concentration of the base times the volume of the base in milliliters, we get 2.5 millimoles divided by 20 milliliters. So our concentration, or our molarity of our acid, is 0.125 molar. And now for what turned out to be the challenge problem. So I gave you 5 steps to get to the pH. So step 1 says find the millimoles of hydroxide and hydrogen ion. So we need to know the moles that we used, so before they reacted. And that step I think went well, but let me take a moment and walk you through it, and then we'll go through the other steps. Okay, so here's the math for that. Again, using millimoles saves you a step because it's all going to come out in the wash at the end anyway. And also, just for ease and for me to fit it on the screen, I did not use sig figs, but keep track of your significant figures as you go. So if we go back and we look at the problem, we have 4 sig figs and 3 sig figs to worry about. So your answers, you should be looking at 3 significant figures as you go through. But again, just for ease of getting the calculations done, I did not do significant figures. Okay, step 2 asks you what's happening in the beaker. So I really want you to take a moment to visualize what's happening. So what's the pH after 30 milliliters of 0.1 sodium hydroxide has been added to 20 milliliters of 0.125 molar hydrochloric acid? So in our beaker, we have 20 milliliters of acid, and then to that, we're going to add 30 milliliters. So this is our beaker when we're done. We're going to add 30 milliliters of base. So what's going to happen with the acid and base, especially with regards to the moles? So that's what you want to think about. They're going to neutralize, hence the neutralization reaction I gave you for number 2. But are they all going to neutralize? So that's where we want to find out the number of millimoles of hydroxide. Now, why did I say there's going to be more hydroxide in there? Why are we looking for hydroxide and not hydronium? Well, if we look at what happens, we have 3 millimoles of that we used, and we only have 2.5 of hydrogen. So we are going to run out of hydrogen and have hydroxide left over in that beaker. So take a moment and see if you can't think through number 2. Okay, so we walked through that, and hopefully you realized that we're going to have half a millimole of hydroxide left over, or 0.5 millimoles of hydroxide, because 2.5 millimoles of hydrogen is going to neutralize 2.5 millimoles of hydroxide. Step 3 says to find the concentration of our hydroxide ion now. Think about what was in the beaker. I had 20 milliliters of acid and 30 milliliters of base. Our volume changed. So what will the concentration be if I have 0.5 millimoles and the volume? So once you get to this point, it should be smooth sailing. Be careful on your division. So you should be able to divide tens or tenths fairly easily, and note that that's going to be 0.01, not just 0.1, which gives us our concentration of hydroxide at 10 to the negative 2. So at this point, not very difficult to do, find the pH and the pOH. So the pOH is going to be 2, and our pH is going to be 12. Okay, so go through that one, spend some time. This could be a nice, easy multiple choice one that you could do without a calculator. So you should be able to do something like this without a calculator. All right, hopefully this was helpful.